Welcome. This is a time series analysis course. My name is Nicoleta Serban. I'm associate professor in the Stewart School of Industry and System Engineering. This lecture is on ARMA modeling, and in this lesson, I will continue the introduction of the estimation of ARMA model with order selection and residual analysis. The first approach uses a modified version of the ACA-ICI information criterion AIC. In the regression analysis online course, you will find an entire lecture on model selection. The AIC approach is one of the most common criteria for selecting among multiple models. It applies in particular to order selection for orders in ARMA modeling, since AIC is a likelihood-based criterion because it's equal to the log likelihood function plus the complexity penalty. For ARMA models, the complexity penalty is different from the penalty commonly used for the classic AIC approach, and is provided here. This modification of AIC has been shown to improve on the order selection over the classic penalty. The approach to order selection is as follows. Fit ARMA models with varying AR orders 0, 1 up to P and varying MA orders 0, 1 up to Q jointly, and compute AICC for each combination of orders and select the orders with the smallest AICC value. If the maximum orders P and Q are large, this can be quite computationally expensive. A much simpler and less computationally expensive approach is the so-called extended autocorrelation function, or EACF, which was introduced by Tsai and Tiao in 1984. The ACF derivation is a two-step approach. In the first step, we first fit an ARMA with order K, where K is the maximum AR order. Based on this fit, obtain the model residual RT, then regress RT on the lagged xt variables xt-1, xt-2 up to xt-k, and the lagged variables of the residuals rt-1, rt-2 up to rt-j for j from 1 up to a large j value. For this regression, we obtain initial estimate for coefficients for the coefficients of the AR of order k and MA of order j. In the second step of the EACF, we improve upon the estimation of the coefficients by obtaining the residuals by extracting from xt the AR part, but with the estimated coefficients from the previous step. The sample ACF of these residuals is referred to as the extended sample ACF. Tsai and Tiao summarize the information in the EACF table. The element in the kth row and jth column is AX if the lag j plus 1 sample autocorrelation of these residuals is significantly different from 0, where statistical significance is established using the confidence interval of the ACF. This is the EACF for an ARMA 1-1 model. Again, X corresponds to statistical significance and 0 corresponds to lack of statistical significance, or that the ACF is plausibly 0. In this example, we see the first 0 at AR order 1 and MA order 1 as expected for an ARMA 1-1 model. Then we see zeros all through the MA orders corresponding to AR order 1, indicating no improvement in MA order from order 1. The same, we see zeros through all the AR orders when MA is order equal to 1. The sample EACF will never be this clear-cut in real practice. In order to assess the goodness of fit, we can assess the model assumptions using the residuals in a similar manner as for residual analysis for linear regression models. Because the variance of the residuals is not constant over time, it is important to standardize the residuals. Moreover, it may be useful to rescale the residuals to identify outliers. For example, how can we use the residuals to assess goodness of fit for an ARMA model? The properties of the residuals should reflect the properties of the underlying process ZT. In particular, the residuals should be approximately uncorrelated if ZT is white noise, independent if ZT is independent, or normal if ZT is normal. If we want to establish whether the residuals are uncorrelated, then we can use the sample ACF and PACF plots along with hypothesis testing procedures. One hypothesis testing procedure is the portmanteau test based on the sample autocorrelation of the residuals as on the slide. Also, the Lewin box test is a slight variation of the portmanteau test while the Lee test is based on the sample autocorrelation of the squared residuals. In order to evaluate the goodness of fit with respect to a distribution, for example, normal, we can use the quantile plot, which contrasts the quantiles of the distribution, for example, normal, versus the quantiles of the process of interest, in this case, of the residuals. I usually recommend to accompany the QQ plot with a histogram of the residuals for a more detailed assessment of the distribution of the residuals. In summary, in this lesson, I introduced methods for order selection and for performing residual analysis in ARMA modeling. Thank you. Welcome. This is a time series analysis course. My name is Nicoleta Serban. I'm Associate Professor in the Stewart School of Industry and System Engineering. This lecture is on ARMA modeling, and in this lesson, I will illustrate ARMA estimation and order selection with a data example. In this lesson, I'll return to the emergency care data example used to illustrate basic time series modeling. In this example, time series models can be used to forecast future ED patient volume based on the estimated effect of predicting variables, and such forecasts can be used for proactive bed and staff management and for facilitating patient flow. A number of factors can influence daily ED visits, and a patient's visits forecasting model should include those factors. Previous studies have shown that ED visits present cyclical variations according to calendar variables, such as day of the week, time of the year, and the occurrence of public holidays. The objective of this analysis is to develop models for identifying temporal patterns and for predicting the volume of patients in an emergency department. The data consist of daily number of patients seeking ED care in a hospital in Georgia in the United States. The ED volume was observed over a period of more than 5 years from 2010 until about mid-2015. In this study, we'll consider temporal factors, although other factors can be used, for example, external factors such as temperature, rainfall, major holidays, school season, and among others, along with hospital data, for example, the percentage of patients seeking care in ED who have public insurance. In the previous lecture, I illustrated how to estimate the trend and seasonality for this particular data example. Note that we applied the modeling of the time series on the transform time series, since the observations in the time series are counts, and thus with the Poisson distribution, potentially indicating non-constant variance over time. The model I selected here to use for removing the trend and seasonality is the model using the non-parametric trend estimation using spline smoothing, along with modeling monthly and weekly seasonality. Specifically, I'm using the GAMR command available in the MGCV library to feed the trend and seasonality. For this, I define the vector of equally spaced time points along with qualitative variables specifying the month and day of the week for each observation to be all integrated into the estimation of the trend and seasonality simultaneously using the GAM function. Last, we take the difference between the transform volume ED volume counts and the estimated trend and seasonality to obtain the residual process to be further analyzed using the ARMA modeling. Note that here we estimate the trend and seasonality in order to reduce the time series to a stationary process. So we want to eliminate the trend and seasonality, and we'll analyze the residual process using the ARMA modeling. Let's take a closer look at the ACF and PACF plots to assess stationarity. The ACF plot on the upper plot and PACF is on the lower plot. For both, we see that a relatively small number of lags have large sample ACF and PACF values, indicating that the trend has been removed. For evaluating the performance of the model for removing the seasonality, we need to plot the sample ACF for a larger number of lags to capture 2 or more seasonality periods. Next, we'll fit an ARMA model only. The R function is AR, with the input consisting of the time series, the residual process in this case, and the maximum order for which to fit an AR model. Here, the maximum order is set to 20. In order to view the content of the output of the model fit, you can use the summary command. To get the order selected for the best fit according to AIC, the value is mod $order, and it's equal to 6 for this model. I also plotted the AIC values, but on the log scale to better see where the minimum of AIC is reached. Again, the selected order is 6, as also shown by this graph, since AIC is minimum for this order. Let's consider the property of stationarity and whether the fitted model is a causal process. For that, we need to extract the roots of the AR polynomial and check whether they are not on the unit circle, indicating stationarity, and whether the roots are all outside of the unit circle, indicating a causal process. To get the roots, we can use the R command pull the root along with AR coefficients, with the first value being 1, corresponding to xt, and the negative values of the AR coefficients corresponding to the lagged xt. These coefficients correspond to the AR polynomial as defined in a previous lesson. We can then draw where the points of the roots are on the xy graph along with the line of the unit root circle for comparison. Assess the residuals for stationarity and other properties. For this, we first extract the residuals from the fitted model using mod $resid, and then plot the residual plots and the ACF and PACF plots of the model residuals and the QQ normality plot. Here are the residual plots. The residual plot does not show to have a pattern. The variance of residuals is also constant. The ACF plot has only the first lag equal to 1, where all others or other values for other lags are small within the confidence band of the sample ACF. The same for the sample PACF. The values are all within the confidence band. The QQ norm plot shows a tail on the left. Further, we will fit an ARMA model, not only an AR model. The R command to fit an ARMA model is ARMA, where we specify the time series, in this case the residual time series, after removing the trend and seasonality. We also need to specify the orders for the AR and MA components of the model. For this fit, I'm using order 6 for AR, as specified by the best AR model fitted previously, and an order 1 for the MA part. Last, we can specify the estimation method if we specify ML. This means that we fit using maximum likelihood assuming normality. Last, let's look at the residual plots for this fitted model. Here are the plots. The residual plot does not show to have a pattern. The variance of the residuals is also constant. The ACF plot has only the first lag equal to 1, where all others are small within the confidence bands of the sample ACF. The same for the sample PACF, the values are all within the confidence band. The QQ norm plot shows a tail on the left. These are similar observations from fitting the AR model alone. It is not surprising since we only added an MA1 part to the AR6 of the model. Note that the orders used in fitting the model in the previous slide are not necessarily better in terms of model fit than other orders. In fact, the question we like to address is, what are the orders that provide the best fit?
We can apply the two methods discussed in the previous lesson. The first method is the simple EACF approach, which can be implemented in R using the EACF function available in the TSA library. The input of this function consists of the time series along with the maximum AR and MA lags for which to obtain the EACF. The EACF for the residual process is here. The EACF is provided for up to 6 lags for both AR and MA components as specified in the implementation of EACF. The EACF does not provide a clear-cut order selection. The first 0 is for AR order 1 and MA order 1, but there are other MA orders for AR order 1 for which there are non-zero EACF values, and there are other AR orders for MA order 1 for which there are non-zero EACF values. After AR order 4 and MA order 1, we see all other EACF values are 0 except for 2 cases. There is not a conclusive order selection using ACF. We can also select the orders using the minimum AIC. For this, we need to fit the ARMA model for all combinations of AR and MA orders up to a maximum order for both. Here I set the maximum order to be 5 and consider orders from 0 to 5 for both the AR and MA component. Note that I specify here n order equal to 6, but that means I consider the order from 0 to 5 as specified in the definition of P and Q. I loop over all combinations of the orders and fit the ARMA model, then save the AIC values in a matrix. Next, we obtain the P and Q orders for which we have the minimum AIC value. The AR code provided first labels each AIC value with its corresponding P and Q orders. Then, the which command finds the index in the vector of AIC values, where the minimum is then extracted for the orders for this minimum and from the P order and Q order vectors. The selected orders are P equal to 5 and Q equal to 5. The larger orders allowed. Last, we fit the model for the selected orders, called here the final model. These are the residual plots for the ARMA 5 and 5 fitted. The residuals do not improve or change significantly from the smaller models AR6 or ARMA 6.1, suggesting that a smaller model than the one selected using the AIC approach may perform similarly in terms of goodness of fit and thus preferred over the selected ARMA 5.5. Less complex models, in other words, those with smaller AR and MA orders, are preferred to avoid overfitting or to obtain better predictions. One of the assumptions that is particularly important when modeling time series is whether the residuals from the model fit are uncorrelated. For such a test, the null hypothesis is that the residuals from the model fit are uncorrelated versus the alternative that they are correlated. Thus, for such tests, we seek large p-values. In the previous section, I provided a brief account on several testing procedures for uncorrelated data. Here I will illustrate how to implement 2 of them, the box-Pierce test and the box-Lewin test. The R command used is the box.test with the specification of the time series to be tested for correlation, the maximum like to be used for the test statistic, here the sum of the 2 orders plus 1. Also, the type of the test, here I specify both the box-Pierce test in the first line and the box-Lewin in the second line. And last, the degrees of freedom of the fit, which is the sum of the number of orders. I applied this test for both the ARMA 5.5 final model as well as for the smaller ARMA 6.1 model. This is the output for this implementation with a summary of each of the tests. The p-values are all large, indicating that the null hypothesis of uncorrelated residuals is plausible. Thus, according to this test, both models perform well in modeling the temporal correlation in the time series process.
In summary, in this lesson, I illustrated ARMA modeling, estimation, and order selection with the example where we're interested in modeling the time series of the emergency department patient volume. Thank you.